details to confuse you. Okay, so let's start with our distortion estimate. So part 1. So we're going to talk about this Berthelot-Dupont distortion theorem. Let me just write the title. Right. So in general, what is distortion, right? So we said yesterday that if we consider a holomorphic endomorphism with CPK, the dynamics is not conformal if K is greater than 1, strictly greater than 1. Then if you take a ball, right, and you iterate backwards, you look at pre-images, you want to estimate how much this ball is to get distorted. So that is to say, for the inverse of this holomorphic maps, you want to estimate what is the distortion or what is the derivative bounds, right? So let me start by writing down some definitions. So basically, the theorem is very long and it's projected on the screen. You can take a look, but after I write down the notations, I will guide you through the theorem, so how to read this theorem. So let's fix a new, like yesterday. So this is F invariant ergodic probability measure with positive Lyapunov exponents, which means every Lyapunov exponent is positive. And we denote by so these numbers are important. Chi1 is the largest, Chi2, and all the Lyapunov exponents with multiplicity. So you know by this, the Lyapunov exponents with multiplicity K1 to KL. Okay, and now I want to consider the space called O. Okay, so what is this space? So this is basically the space of orbits. So because holomorphic endomorphisms are not invertible because it's an endomorphism, right? So we need to consider the space of orbits or the natural extension. So this is the sequences of points in CPK where the next one is the image of the previous one. So basically, the natural extension. So if we have this measure downstairs, which lives in the dynamical system of F, we can lift, so it's a standard thing in dynamical system, we can lift this measure to the space of orbits. So I'll let nu hat be the lift of nu to the space of orbits. Okay, so now I think I still need to introduce a bunch of notations. Okay, so these are notations required for the theorem above. So I would denote by C of F the critical points of the set of critical points of F. Okay, so what is this collection? So this is the collection of points in CPK such that this matrix, the derivative matrix, is not invertible. And this is a codimension 1 condition, right? So basically, the set of critical points is a hypersurface in CPK. So in particular, when K equals 1, the situation is simpler. So the critical points is a finite collection of points, but in higher dimensions, it is a surface, hypersurface. It's not invertible. Okay, and then I want to define a subset of O called Z, and this is the Z appearing over there. So this is the collection of X hat in the natural extension so that the orbit does not touch critical sets. So Xn is not in the critical set for all n in Z. Okay, and in particular, so since our measure has strictly positive Lyapunov exponents, so the measure mu of the critical set is equal to 0. And in particular, the nu hat measure of Z, so this is a full measure set with respect to nu hat. Okay, and then, yes, I want to define this map. Okay, so what is F minus N x hat? So this is a way of specifying an inverse branch of this holomorphic endomorphism. So basically, you want to iterate backwards by N. Since F is not a D-field, it's not invertible, you need to specify which branch you're taking. So this x hat is an orbit. So basically, this is the inverse branch taking x0 to x minus n, right? So you start from a point in Z, and you specify after n steps where I am. So this inverse branch is unique, right? So once you specify what is x0 and x minus n, then you know which branch you are taking. Okay? So this is the map appearing in the commutative diagram, like the box over there, right? Okay, so now let's read the theorem. So this theorem is the starting point of our distortion estimate. So this is also the place where we use the fact that the map is holomorphic, right? Because we want to get through these distortion estimates. So this theorem is due to Berthelot-Dupont, where they use complex analysis to get these results. So if you wonder, can you get these results without using the holomorphicity of the map? You can do it yourself. But we took their theorem, so we need to require the map is holomorphic. Okay, so what does this theorem say? Okay, so it says blah, 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 blah. And then so the starting point, is really the commutative diagram in the below, right? So if you look at this rectangle, so you start with a ball, centered at x0, a point, and our x hat is some radius, and you want to map this ball by this inverse branch. So basically, you are taking the inverse image of this ball, right? And since this is a commutative diagram, it basically says the map from the ball to its inverse image is equal to the composition of the other three maps, okay? So what are the other three maps? So the first map is number 2. So there's a sequence of phi x hat n. These are injective holomorphic maps from these balls to disks. And then you map by this L x hat n to another disk. And what are their properties? So because these maps are nice in the sense that we can estimate, right? Yes?
What is the d to the k notation?
It's a unidisk to the power of k. Yeah, it's like a polydisc.
So it's going to be k complex.
Yes, exactly, because
the radius.
yeah, exactly, right.
Sorry, is it a product of disks or is it
Product of disks, yes. So, right, so basically you want to compose these three maps, and the estimate of each map is given above, right? So for phi, or phi inverse, the estimate is in number 2, and this L is particularly nice. It's a linear map, so basically it stabilizes the inner subspace, right? So basically, if you take this theorem tells you roughly how to compose these three maps to get an estimate for the inverse branch. Okay, so but this is not exactly so trivial. So let's take this. Okay, so I want to define another set called Z sub nu. Okay, so this is the subset of Z. Okay, so if you look at the statement, there's nu hat almost every x hat in Z. So this Z sub nu is the collection of x hat in Z satisfies the distortion theorem. Berthelot-Dupont distortion theorem. So why? Because we can only do estimates in this set, in this full measure set, right? Because that's where it says. Okay, so now I want to erase everything there, and let's start with the real content. Yeah, it's at least it's not a contraction. Yes. It's a linearization. Yes. Mm-hmm. Yes. 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 I think eta is very small. Yeah. So basically, it's like it's up to some controlled arrow. Yes, because there's the bound. Yes. 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 So yeah. So basically, like it stabilizes like oscillator subspaces. Okay. So basically, like what does this theorem say, right? So basically, like if your system is uniformly hyperbolic, you iterate backwards. You expect things to kind of like behaves like e to the minus n Lyapunov exponents, right? So this is basically says it's almost like that, except you have some arrows, like n epsilon arrows every time you iterate, right? Okay, so number 2, we want to define something called dynamical ellipse. Okay, so dynamical ellipses and their estimates. Okay, so you take a point in this set where you have this distortion estimate and take a natural number n. So we want to define the dynamical ellipse which I will denote by E, x minus n, and you put some parameters like the radius or the length of the axis, so R1, R2 to RK, and then in application we're putting these numbers, so it will look something complicated. Okay, so this is defined as the first map is coming from over there. So it's the phi map, right? And you compose with big phi of the uniball to the power of k. Okay, so what is this big phi map? So where this big phi map is a map from ck to ck, linear, where this is a linear map, such that phi of Ej at x is equal to Rj. Rj is the radius you specify times Lj of x. So what is Ej and Lj? So Ej is a standard basis. So basically you pick a basis for ck. And these Lj's are going to be the basis for the oscillator splitting. Okay, so that is to say, this Lj x is a basis of the tangent space at x, such that the span. Sorry, maybe let me write Lj x. So what is Ljx? So Ljx is from yesterday, from the Lyapunov exponent or oscillator theorem. So this is the span of the vectors Ljx to Lk x, right? I think that's basically true. Yes, so basically like this set E is one set. So what is the goal? The goal is we first study what is this E set, and then I will, which by definition is this guy. We want to study their estimate. So in particular, we want to estimate what is their, I think, volume. What is the volume of this? And part number 3, I'm going to define the mysterious set U epsilon x k n. And we're going to show that if you take a U x epsilon kappa n set, it's going to be inside a dynamical ellipse, and also it is contained in a dynamical ellipse, and also it contains a dynamical ellipse. So that's how you can estimate. So it's like in a conformal dynamical system, you take a ball, and the pre-image of a ball is containing a ball, and it contains a ball, right? So this is like something. Yeah, so basically like, so you want to specify what is the radius. So we will see what is our application. And in particular, when the Lyapunov exponents are the same, then this is basically a ball. Ellipse becomes a ball. Okay, so yeah, let me just write down estimates. Okay, so I want to write this as a corollary. So this is a direct corollary of this distortion theorem, except you need to do a lot of computation. So corollary, so for any epsilon bigger than 0, but much smaller than the smallest Lyapunov exponent, which is this L, right? Oh, I just erased. Anyway, smallest Lyapunov exponent. So epsilon is sufficiently small. There exists another set. So this is Z nu star epsilon in this Z nu set. And also there exist two numbers, n epsilon, natural number, and r epsilon. So basically like n plays the role of Wheeler-Ritz, and r plays the role of radius. So this radius is between 0 and 1, such that the following holds. So number 1, the measure of this Z nu star epsilon is bigger than 1 minus epsilon. So, and also this nx hat. So basically this nx hat in the distortion theorem depends on x hat. But now I want to make the estimate uniform by putting an epsilon level structure. Okay, so this is smaller than or equal to n epsilon. And r x hat is greater than or equal to r epsilon for any x in this level epsilon set. Okay. And number 2, so for all the parameters which we're going to put, so some scale. And you take a ball. So basically these, we want to prove something like boundary distortion, and also estimate what is the volume of these dynamical ellipses. So number 1, yes, so the Jacobian of this inverse branch at the point y, so you take 2 points in the ball, right? And then basically like this is to say their derivatives are bounded. So you divide by the Jacobian of this inverse branch at w. This is bounded above by e k n epsilon, and bounded below by e to the minus of this number. Okay, and number 2, so this dynamical ellipse. So inverse image of a dynamical ellipse is contained in another ellipse. So e to the minus n kj plus epsilon. Okay, so now I stop a little bit. So now this is our first application of plugging, like, what is the radius for dynamical ellipses, right? So here I wrote down the definition that you need to plug in some numbers, right? So this is the number we're plugging. So it's Tj. Tj is kind of like a scale, and times r epsilon. So for this radius uniformly at the level epsilon. And then e to the minus n, chi j is the Lyapunov exponent. So for the jth coordinate, you plug in the jth Lyapunov exponent plus epsilon. Okay, so it's like for the first coordinate, you plug in r1. R1 is you plug in chi1, and with this crazy number. And the second coordinate, r2, you plug in this number with tj, so t2, and here is chi2, and then you do it. Okay, so this is the ellipse. So this one is contained in the inverse image of a dynamical ellipse, kind of like, yes. So if tj's are the same, this is the ball, right? So this, and then it contains r epsilon e to the minus n chi j minus epsilon. So basically, like, we want to estimate, like, if I start to iterate, right, like how things are distorted. Like if I have these radii, and then what do I get, right? And then this is number 2. Number 3, also you have, if you have a ball, so t r epsilon e minus n chi j plus epsilon is contained in, this is a ball, that's x0, t r epsilon. So x0 is the zeroth position of x. Okay, so this is contained in this x minus n, t r epsilon, e to the minus x chi j minus epsilon. Okay, so this one is similar to this. And then what are the volumes? So B and C should also comes with volume. So, okay, so let's try to write here D. So this is T R epsilon. So basically, we already know it's contained in this ellipse, and then we calculate what is the volume. So this is K dimension, e to the minus 2n, sum of Lyapunov exponent times K epsilon, smaller than or equal to volume, Fubini-Study volume of this ellipse, e to the minus n times chi j, right? For 2k, e to the minus 2n, Lyapunov exponent minus k epsilon. So basically, like, you always get this kind of controlled error. So that's the key. So basically, you want to estimate what is the volume. It's basically like minus sum of the Lyapunov exponent, but there's some like nk epsilon. Okay, so A, B, C, D, E. What is the volume of f minus x of x? So if you know where they are contained, you can calculate the volume, right? So okay, so these are the estimates, and I said the proof is, since this is a corollary of the Berthelot-Dupont distortion theorem. So I'm not going to show the calculation. Yes. Here. For n bigger than this n epsilon. Yeah, you want n to be large. Yes. Yes, so basically, yeah. Okay, so basically, like, we first define what are the dynamical ellipses, and we'll have estimates of what are the distortion on the Jacobian, and also like where they go under iterations, and also what are the volumes. Okay, so now I'm gonna maybe erase there. So finally we get into this interesting set, this U, X, K, sorry. Let me just write. So number 3, the U sets and their estimates. Okay, so what are these sets? Okay, so we first define a number, which is called M. So this is log of, you take sup over all the points in the projective space, and all the tangent vectors. It's k of the derivative. So it's like estimate how big is the derivative. So the norm of this vector divided by the norm of this vector. Okay, so this number is called M. So basically, e to the power of M is a bound, upper bound for the Lipschitz constant, right? So basically, if you have a ball at x0 of radius r, then this image is going to be contained at the ball at f of x0, right? And e to the power of m times r, right? And then this is for every x and every r, right? So basically, this one dominates the Lipschitz constant, or it plays the role like Lipschitz constant of f. Okay, so it's like at most how large f expands things. Okay, so now, yes, I'm going to write down the definition, which is kind of, it's very simple to write down, but it's kind of fake, because it's not always defined if I just write down like this. Okay, so if we have a natural number n, greater than or equal to 0, and I take a point inside my projective space, and I take a radius kappa bigger than 0, and I take epsilon bigger than 0. So epsilon is the level, right? Then I define this U set, so n x kappa epsilon. I define this to be such that, so this is a set which satisfies the following property. There are two properties. So the first property is, but basically, like, if I take f to power of n of this, I get a ball. Okay, so f to power of u. So if I call this set simply by u, so if I take the nth iterate and then the image of this set, so this is a pre-image of a ball, right? So, but what is this ball? So this may not be the ball you think what it is. So the center of the ball, you may guess, right? So it's fn of x. But what is the radius? So the radius is not these numbers. So the radius is kappa, but it's not kappa or e to the m kappa. It's kappa times e to the minus n m epsilon. Okay, so these are the sets we're using. So basically, you take sets like this, and you take the nth pre-image. Okay, and also we require that the restriction of f to nth iterate of f is injective on u. Okay, so these are the sets that we take. So this is the definition of this set I wrote down yesterday. So this kind of plays the role of Bowen ball, right? Kind of, except maybe like here the radius is not very standard. Yes, so what do we want to do? So there are some problems if I just write it like this, right? So basically this n is not super correct because if you pick around n, you may not apply these estimates. So basically we need to put n, x, kappa in these sets where we can estimate, okay? And exactly, I'm gonna write out what is the estimate for the U sets. Yeah. Oh, which one? Like here? Oh, m is here. Yes, so it's kind of like e to the m is the log of Lipschitz constant. M is log of Lipschitz constant. Okay, so any other questions? So I'm gonna write down another bunch like this, except some of this will become U, okay? So in particular, we want to say like the nth iterate, the backward of U, you look at the nth preimage of U, is going to be contained in a dynamical ellipse, and also it contains a dynamical ellipse, right? So that's how you can estimate what is the volume of these sets. Okay, so let me just erase this corollary. So the corollary is important because the statement will go into the proof of the lemma that I'm gonna write down. And also, I'm not going to write out the proof of the lemma. Okay, so, but the lemma is going to be the key lemma because it tells us what is the estimates, right, of these U sets. Okay, so lemma. So there exists an exhaustion, which is the epsilon structure, the epsilon structure that we put on Z nu star, right? Exhaustion. Z nu star, epsilon, and epsilon bigger 0 of this set Z nu, right? So this subset of the space of orbits where we can apply this theorem. So this is a full measure subset of Z, all right? Okay, so there's a exhaustion by putting this epsilon level such that Z nu star epsilon goes to Z nu as epsilon goes to 0. Okay. Okay. Maybe with such that for each fixed epsilon with 0 smaller than epsilon, smaller than the smallest Lyapunov exponent, there exists n epsilon, so coming from the corollary, and r epsilon between 0 and 1, such that for every x in pi, which I haven't said what is pi, pi Z nu star epsilon, and n bigger than or equal to this bound, and kappa between 0 and this r epsilon, the set. So basically, like this pi is the projection from the natural extension down to the dynamics, right? So let me just write it like this. So pi is from O back to pk, right? So O is a space of orbit, and then it basically gives you x0, okay? So basically you project this set down to the projective space. So the set U, x, n, x kappa, epsilon is well defined, and we have estimates. What? Oh, that's a good question, because yes, in our paper there's the new start, because I omitted some details. There's another technicality. So because yeah, so this set is basically like where you can apply. Yes. Okay, it's well defined, and we have 3 estimates. So number 1. We want to say this, as I said, these U sets is contained in an ellipse, and you know what is the radius. So for every coordinate, you plug in kappa, where kappa is this kappa, where is this. You want to iterate backwards, right? Okay, kappa to the power of minus n, Lyapunov exponent minus epsilon, okay? And then the other one is you take plus epsilon. Nope. So this one is more complicated. So 2m plus 1 epsilon. Okay, so it's a little bit asymmetric, so I missed a bracket. Okay, so you look at the exponent, it's roughly Kj plus epsilon. So this is due to another layer of technicality I omitted, so it's not just Kj plus epsilon. So this is Kj minus epsilon, and this is Kj plus epsilon. So Kj means, again, like for the jth coordinate, you put Kj. So the first coordinate is K1, and then K2, K3, blah, 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 right? Okay, so yeah, so these U sets, the pre-image of walls is contained in a dynamical ellipse, and it contains a dynamical ellipse. So here you can see, right, when all the Lyapunov exponents are the same, so this pre-image of balls is contained in a ball, and it contains a ball. So it's a conformal situation. Okay, so number 2. What do we want the volume. So volume of kappa epsilon is smaller than or equal to kappa to the power of 2k dimension, e to the power of 2n, Lyapunov is sum of Lyapunov exponents, subtract k epsilon. So here the k in the exponents are dimension. Okay, so downstairs are radius. So this is e to the power of negative n, 2m plus 1, k epsilon. Sorry. Ooh. Let me erase here. So this is kappa, 2k, e to the negative 2n, sum of the Lyapunov exponent, plus k times 2m plus 1, so this number, epsilon, right? Yes. Okay. So basically, like, if you know they're contained in the ellipse, right, you can calculate the volume of these ellipses. So you know the volume of these guys are bounded like this. Okay, so also number 3, the Jacobians are also bounded. So let me start here. So Jacobian, Fn of y times, or divide Jacobian Fn of w, okay, is bounded by e to the power of n, 2m plus 1, k epsilon, for any y w inside this U set. Okay, and then there's a lower bound. So e to the minus n, 2m plus 1, k, and epsilon. Okay, so basically this is saying, yeah, what does this say, right? So basically you first put a level to exhaust this full measure set z sub nu, and then at level epsilon, right, all the estimates are uniform. So you have a uniform bound on the iterate. So the iterate should be bigger than this bound, and the radius should be smaller than this bound, such that for these x, these n, and these radius, the set is well-defined. So like here, I just formally wrote down what these sets are, but it's not going to work for every n x kappa epsilon. Okay, and also once it's well-defined, we know where they are under iteration. Yeah.
In this lemma, do you have to worry about the use having?
No. So basically, like this also embeds into theorem 2.1. Yes. So. Yeah, so because there's no constraints on the map. Yep. Yeah, so there's constraints on the Lyapunov exponents of the measure. This is because, like, I guess, like, for this audience, like, people know more because, like, if you have some Lyapunov exponents which are negative, or like, there's some resonance problems that these guys couldn't get their estimates. So anyway, like. That's also like why we require all the Lyapunov exponents are positive. Okay, so yes, so I will, yeah. So this is the end of the lemma. So what is the proof of the lemma? The proof of the lemma uses the corollary I just erased. And again, I'm not going to write out the proof. The proof is well, it uses a corollary, but it involves a lot of computations. You need to iterate a lot of times to see which one is contained in which, and then what are the volumes. But this is kind of the key estimate and gives you an idea of the dynamics, right? So, okay. So now, I think I have 80 minutes. So now I'm going to define the exciting thing, finally. What is the volume dimension? So basically, the volume dimension is going to be similar to House dimension, except you cover the set by these U sets. And for House dimension, you have a cover, right? And you take every element in the cover, you take the diameter raised to power of alpha. And in the volume dimension, you take these sets as cover, as elements in the covers, and you take their volume to power of alpha. So that's how we can estimate. Okay. Okay. So take a set, a y, in the projected Z nu, right? So basically, like this is a setting, subset of PK, and it's the lift is in the good set. Okay, so and the epsilon bigger than 0 for the level, and then we set y epsilon to be y intersect pi Z nu star epsilon, right? So basically, you intersect y. So you also kind of like stratify y by epsilon. And we're going to cover y epsilon by these u n x kappa epsilon, because here you have an epsilon. So you need to first make your set y to have epsilon, right? So it's here. So we have here the epsilon. So that's why, like, you need to first make your y epsilon. Okay, so now I'm going to define something that is similar to House dimension. Okay, so first we define a quantity, lambda alpha epsilon y epsilon. So this is defined as lim sup as kappa goes to 0, limit n star goes to infinity of info villa covers, and sum as ui in the cover, so sum over I. Okay, so now, as I said, we want to take the volume of ui to power of alpha. Okay, so the difference is here we take volume, and also what are these? ui, right? So these ui's are u, but you have ni x kappa epsilon for some x in pi z nu star epsilon, and ni is bigger than or equal to this n star, and you take n star to go to infinity, and n star is bigger than this n epsilon. Okay, so this is kind of like the first quantity you define when you want to study house dimension, right? And then you prove this function as a function of alpha. It has the kind of like a critical exponent. It has the cut. Okay, so number 2, well, after you know how this quantity behaves as a function of alpha, you can define the second one. So we define the volume dimension at level epsilon. F nu epsilon of y epsilon to be the sup. So basically, like this function as a function of alpha, like lambda as a function of alpha, it's going to be like the same, right? Lambda epsilon alpha, and then it's going to be infinity for a while, and then it becomes 0. So basically, like this is the dimension. So sup, yeah. Oh, y epsilon is a set. So you want to say, okay, I take a set. What is its house dimension, right? Oh, y, you intersect y with this subset. Ui. So this is a set. You want to cover this set by ui. So this is a cover, like ui. You want to cover this y epsilon. Yes. Okay, so maybe I should say this is a cover. And then you take inf over all the covers. Yes. Yes. So, and then, yeah, and then you prove something like this. So this requires a proof, right? Because it's a priori some random thing. Okay, so then you prove it looks like this. So you define this dimension to be the sup when this is infinity, and the inf, or the inf when this is 0. Right, so lambda alpha epsilon y epsilon equals infinity, or the inf this one to be 0. And then what is the volume dimension, right? So volume dimension means, because now we're doing everything at level epsilon, so you let epsilon to go to 0. Okay, so volume dimension of sets and measures. Okay, so volume dimension of y is going to be lim sup as epsilon goes to 0 of vd f nu epsilon y epsilon. Okay, so here I write lim sup. A priori it's a lim sup, but a posteriori it's a limit. So we have another way of equivalent way of defining what is the volume dimension, and there you can see it's a limit. But like, let me just remark, this is in fact a limit. Okay, so, and then volume dimension of a measure, right? So this is the house dimension, so this is the inf of volume dimension of a full measure Varroa set. Vd f nu y, okay, nu y is equal to 1, and 1 is a Varroa subset of z nu, pi z nu. Okay. Okay, so this is the definition that we want. And then this guy is the is the guy appeared in the theorem, right? So we said volume dimension of nu should equal to entropy over 2 times Lyapunov exponents. Right, so this is the definition. Okay, so now, how do we prove, right? So why this guy equals entropy over twice Lyapunov exponents? I have 10 minutes, okay. Yeah, as I said yesterday, so the proof consists of 2 steps. Okay, so number 5. Okay, so the proof consists of 2 steps. So first, we need to prove exact volume dimensionality of the measure. And then the second step is kind of like you go through Lai Sang-Yang's paper and see how to change everything so that it works for volume dimension. Right? So I'm only going to talk about the first part, exact volume dimension. Yes, so we want to, so let me just recall the local dimension. Okay, so x is in pi z nu star epsilon and 0 between kappa is between 0 and r, and n is, so basically the radius and the iterates are good, and then we can define the local dimension delta x epsilon kappa n. Right? Because it involves the sets U, so you need these x kappa n to be in the good set or good range. Okay, so this is log of nu, measure of U, and x kappa epsilon over log of volume of U and x kappa epsilon. Okay, so basically this is the a quantity, so the limits is going to be the local dimension. Okay, so what do we want to show? We want to show exact dimensionality, which means for nu, almost every x, we have lim inf, epsilon goes to 0, lim inf, kappa goes to 0, lim inf, n goes to infinity of delta x, epsilon, kappa, n, all the lim sups. I'm not going to write down the downstairs, so this guy. Okay, so this is going to be entropy over twice the Lyapunov exponent. So this is what we want to show, right? And basically, like in the last part, you want to prove the volume dimension is bounded below, like for nu almost every x, bounded below by this number, and bounded above by this number. And then that's how we prove it. Okay, so how do we prove this? Okay, so let me erase more things. So I'm going to write down the theorem. So I'll let epsilon to be in between, for any epsilon between 0 and smaller than the smallest Lyapunov exponent. So then for nu hat, almost every x hat in this z nu star epsilon. So basically, we want to prove the exact dimensional at the level epsilon first. Okay, so and every kappa between 0 and r epsilon, there exist integers. So they are going to be the bound for n. M1, depending on epsilon and x hat, bigger than n epsilon. And M2, depending on epsilon and kappa, greater than or equal to 0, such that we have this delta at x0 of epsilon kappa n is smaller than or equal to this number you want, plus some error. And greater than or equal to this number, subtract this number. Okay, so where C is constant independent of the parameters. So where C greater than or 0 is a constant independent of epsilon x hat and kappa. Okay, so this is, as you can see, like if you take epsilon goes to 0, then you get exact dimensionality. Okay, so how do we prove this theorem? We prove this theorem by proving a proposition. So I'm going to state the proposition, and I will say, like, basically, like, well, like the statement of the proposition will suggest what is the idea, and I will probably explain how to prove the theorem assuming the proposition. Okay, so proposition. So for any epsilon in this range, there exist two partitions, P1 and P2. So basically, one is going to give you the lower bound, one is going to give you the upper bound, with the entropy of the first partition greater than or equal to this measure theoretic entropy, and there are four constants, BE, BF, so these are independent of epsilon, and CE, CF, these may depend on epsilon. Okay, so such that, question? Okay, such that for new almost every x hat, there exists integer m, so this is the number that's in the theorem, such that for all n greater than or equal to m epsilon x hat, we have, so basically you want to say these partitions, the nth iterate or the nth generation of partition contains some ellipse so that you can estimate. Okay, so we have, so I define this set to be e to the n x0 of c e minus n chi j plus b epsilon. So this is, if you look at the nth, so this is the partition generated by P1, F inverse P1, F all the way to F minus n P1. And then this is the element containing x0. Okay, so, and, so P2 and x0. So, and this guy is contained in ellipse, right? So that's how you get two bounds. CF E minus n chi j minus this constant of arrow epsilon. Yes, okay, so this is statement of the proposition. So basically, like, the key is to find these partitions. So the proof of the proposition, so how to find these partitions, well, like, I guess it's not like a super foreign thing in dynamics, right? So basically, like, for P2, it's a kind of Manier partition, right? With so Manier partition, you need to also pick a measurable function, and then you need to decide what is the function you want to pick, so it works. And P1, I think, is also a kind of partition which appeared in the literature already. Okay, you just need to figure out what are the partitions that will give you this. Okay, so so Y theorem follows from this proposition, right? So here, the theorem, we want to prove this delta. So delta is, yeah, so I will just say, like, so delta is log of the measure, right, over log of the volume. So basically, we're going to estimate what is the log of the measure. So log of measure, we're going to use these partitions so that you can say log of the measure, maybe over n, is related to entropy by Shannon, Macmillan, Bremen. And so this log of volume, right? So we have estimate. This is going to give you Lyapunov exponents. So it's entropy over Lyapunov exponents. I mean, this is a fake proof, but how much time? Oh, I don't have time. So, sorry. So, yeah, but it's good not to write out the proof. There will be like lots of estimates, even though I already omitted some details. But yeah, as I said, so the proof is to use these partitions to say, maybe let me just write down. So this set, so the key is to get to this. So you have a U, which is contained in some specified iterate, like n. You need to cook up what is this number, okay? And then this one is contained in P2, NF. So this part is given by the proposition, okay? So this part is given by the lemma that I said before. U is containing ellipse and is containing another ellipse, okay? So this is containing x0. Okay, so let me just erase here a little bit. And then this is contained in the other partition, an E of big N epsilon. Okay, and then this is contained in P1 of N E, containing the point, 0. So basically for all, anyway, for all N large, and some numbers. Okay, so basically, like once you get this, as I said, you can use Shannon-Macmillan-Bremen to say like log of the measure of the set divided by n, or negative log of the measure of the set divided by n, is smaller than or equal to entropy. And then here, the denominator is going to be Lyapunov. So that's how you prove these bounds, right? So like it's the top is entropy, the lower is Lyapunov. Okay, so I will stop here. Thank you very much.
Are there any questions?
What role does the inverse limit actually play in the proof? I mean, you used it as a...
Yes, in the definition of U, right? The inverse image of ball.
I understand that, but I mean, was it, I mean, you know, is it really used, or you could have done without the inverse limit? I mean, does it...
You mean inverse limit or
The
inverse
natural
branch?
extension.
What's that?
The natural extension.
Oh, because you want to specify inverse branch, and also, yes, and these estimates, you see the hats are all in the natural extension, because your map is not invertible, so you need to specify like which branch you are taking.
No, I work with inverse limit a lot, but it seems to me that it's just a tool that you use to, but is it really used as a main ingredient, or
So
it's
that's
just
the space you work with, I would say, yes.
I see.
Yes, yes, yes.
Okay.
Thank you. I'm wondering what's the motivation that you use volume as a gauge instead of usual diameter as a
so
gauge,
I think
and
we'll-
other
yeah.
than making this formula happen?
Yeah, that's a good question. So basically, like in dimension 1, right? You basically has like you want to understand what is log f prime. Like f prime is kind of like measuring the expansion on average. So in higher dimensions, you want to replace f prime by Jacobian, and then if you integrate Jacobian, you should get volume. Right.
More questions? Okay, but wait a minute. In the name of the scientific committee, I would like to thank Mary and Fabrizio for this course here. And
Thanks.
let's thank